Hello everyone, my name is Sebastian and today I'm honored to present my latest research titled Bi-Planar Coil Synthesis for PCB Manufacturing and No-Smooth Convex Approach. In this talk, I will present a novel mathematical and engineering methodology that fills a long-standing gap in the field of electromagnetics. How to synthesize high-precision planar coils while satisfying string no convex physical manufacturing constraint without sacrificing global optimality. The answer lies in the rigorous framework of disciplined convex programming. To guide you through the methodology, I have structured this presentation into 5 main parts. First, I will analyze why designing electromagnetic coils is inherently an ill-posed inverse mathematical problem in the sense of Heidmar. Second, I will discuss how the continuous problem is framed within convex optimization and how the not differentiable no-smooth barrier is overcome. Third, I will confront the manufacturing paradox where physical fabrication rules beyondly threaten to destroy the convex models and demonstrate how to decouple them. Fourth, I will show how this paradox is resolved using a parametric decomposition strategy that leads straight to a multi-criteria Pareto frontier. And finally, I will analyze the simulated layouts, verify the magnetic field quality, and wrap up with the main conclusion of this work. Before diving into the mathematics, let's just look at the physical motivation behind this work. Why do I care about planar electromagnetic coils? They are in fact the quiet engines behind many modern high-precision scientific instruments. A prime example is magnetic resonance imaging. In resonance systems, active shielding coils are integrated into the scanner to counteract external fringe fields and confine the intense magnetic flux strictly inside the board. This magnetic screening is vital to prevent electromagnetic interface with surrounding clinical electronics. Another critical application is precision sensor calibration. As illustrated in the diagram of the right, parallel biplanar coils are used to generate highly controlled, extremely homogeneous magnetic environments. This allows for the testing and calibration on high-sensitive devices like precision magnetometers and quantum sensors under perfectly controlled laboratory conditions. Planar coils are also the backbone of wireless power transfer. Here, coil topologies on printed circuit boards are optimized to maximize the efficiency of inductive energy transfer in consumer devices like mobile phones and others. In all these diverse applications, the engineering challenge remains identical. The exact distribution of electric currents on a plane must be found to generate a specific, highly controlled and uniform magnetic field in a central region of interest. Physically and mathematically, the starting point is the classical Biot-Savart law shown in the block at the top. This equation relates the continuous current density vector on the descent surface to the resulting magnetic field vector at any evolution point in space. From a mathematical standpoint, this integral is a Fredholm operator of the first kind. In the forward problem, this operator is continuous, linear, and compact. You give me a smooth, well-defined current density, and I can calculate a continuous, stable magnetic field. But as a designer, my goal is the exact opposite. The target magnetic field is known inside the region of interest, and this compact operator must be reserved to find the corresponding current paths. This is where I run directly into a mathematical wall. Inverting a compact operator in infinite dimensional space is a classical example of an ill-posed problem in the sense of Heidmar. Two catastrophic mathematical violations are encountered. First, there is a lack of unities. The kernel of the Biot-Savart operator is non-trivial, which physically means that silent eddy currents can circulate on the descent plane without producing any external magnetic field. The mapping from current to file is not bijective. Second, and most critically, there is extreme solution instability. During the algebraic inversion, high spatial frequency noise is exponentially amplified. If indirect algebraic inversion is attempted, such as a standard pseudo-inverse, the calculated current density oscillates violently towards infinity. These giant microscopic loops, overlapping paths, and infinite current densities. In other words, it results in a PCB layout that will instantly melt and is physically impossible to manufacture. I need a different mathematical framework. To change this mathematical chaos, the current density is restricted to a two-dimensional boundary plane under a stationary steady-state condition. Under this condition, the current flow must be a divergence-free, which allows a topological vector transformation to be applied. The two-dimensional vector current density is represented as the curl of a one-dimensional scalar file, which I call the stream function, denoted by C. This is a major mathematical simplification. A complex vector file estimation problem has been successfully reduced into a much simplified scalar file estimation problem. By discretizing the scalar file using the inverse boundary element method, or even the continuous integral operation projects onto a decimal matrix M. This results in a linear algebraic system where X is the finite vector of nodal stream function values. Let's define the spatial geometry of this discretized system in detail. As illustrated in the figure on the slide, a multiplanar boundary configuration is set up. The goal in the inverse reconstruction to find the exact electric current density following on these parallel boundary planes. This current must be synthesized such that it generates a highly uniform pre-specific target magnetic field inside the central volume known as the region of interest. To solve this continuous problem numerically, the parallel planes are discretized. The continuous planar surfaces are meshed into n infinite boundary elements. These projections allow for converting the continuous Fredholm integral equation of the Biot-Savart law into a finite-dimensional system of linear algebraic equations. Here, the decimal matrix M acts as the mathematical bridge. It encapsulates all the physical, geometric, and electromagnetic green function linking the boundary nodes on the planar to the evaluation points inside the central region of interest. The key variables in this discretization model are the nodal state represented by the vector x. Each element of x defines the value of the scalar stream function at a specific node on the boundary mesh. This representation is elegant because the stream function is continuous across the mesh. By solving for the vector x, a continuous surface definition of the stream function is obtained. From this, the physical track layouts can be easily illustrated, completely avoiding the need to optimize the coordinate of individual discrete coil, which would be a highly complex combinatorial search. Let us look deeper into why the stream function is so powerful for physical manufacturing. Because the current flow is stationary and confined to the plane, the magnetic field is linearly mapped by the continuous scalar stream function. More importantly, there is a direct geometry equivalence between the math and the Cooper. The contour levels of the stream function represent the exact physical paths for the Cooper trace on the PCB. Furthermore, if these contour levels are quantified using a constant difference, the net electric current flowing between any two adjacent Cooper lines is strictly constant and equal to that potential difference. This means a complete physical circuit layout can be generated simply by drawing the contour lines of the optimized stream function. By combining the boundary element mesh with the stream function, a powerful paradigm shift in electromagnetic design is achieved. Traditionally, designing a coil meant adjusting the individual shapes and position of discrete wires. This is a highly nonlinear combinatorial shape optimization problem prone to local minima and extremely slow convergence. Instead, this approach shifts the focus entirely. Linear state estimation is performed. I search for the optimal continuous nodal values of the vector x on a fixed mesh. Once x is found, the optimal wire shapes are strictly exposed by taking its contours. This shift yields a smooth, globally searchable optimization landscape. However, one cannot simply solve the linear system directly, because the design matrix M inherits the server yield conditioning of the Biot-Savart operator. A direct pseudo-inverse will yield massive spatial oscillation. The problem must be regularized. Instead of classical Tikhonov least square, which only minimizes the average energy, I propose a minimax formulation. I minimize the absolute worst-case scenario, the maximum local current density across all nodes. This objective is subjective to a strict boundary constraint. The maximum relative file error in the infinite norm must remain below a user-defined tolerance. Mathematically, the presence of the maximum operator at the infinite norm introduces a significant barrier. The problem is convex but strictly non-smooth. Let us analyze the minimax formulation from a modern optimization perspective. As shown on the slide, the objective function is the maximum local current density, expressed using the L2 norm of the current density vector at each node. The tolerance constraint bounds the L infinite norm of the magnetic field derivation. Because both norms are complex functions, and side composing them with a fine transformation preserves convexity, a mathematically beautiful result is achieved. The design space is extremely convex. There are no local minima. However, the supermoon and maximum operators introduce sharp edges in the functional landscape. The objective function is convex, but it is not differentiable at these kinks. Why is this lack of differentiability a major problem? Because classical differential calculus completely fails here. A standard, widely used nonlinear programming solver, such as gradient descent, assume that the functions are continuously differentiable. If this minimax problem is fed to this traditional solver, the algorithm will hit one of these sharp kinks. Lacking a defined gradient, the search directions will begin to oscillate, bouncing back and forth across the edge in an infinite Stalin loop. I must move beyond classical derivatives and leverage modern convex analysis, replacing the gradient with the set-valued subdifferential as defined by the inequality of the slide. To guarantee that this problem can be solved reliably and globally, I strictly adhere to the rule of disciplined convex programming. Instead of manually computing complex set-value subdifferentials or dealing with ill-conditioned Hessian matrices, the optimization model is constructed using a library of basic atomic functions. These functions are combined according to strict, mathematically proven rules of composition and inequality. As shown on the slide, because the maximum current is a valid convex composition and the relative error limit represents a valid convex set, the parser can automatically and deterministically verify that the entire problem is globally convex before the solver even starts. Now, how is not a smooth convex problem solved? A geometric transformation known as conic inversion is performed. By introducing an auxiliary scale variable t, the parameter space is expanded and the non-smooth objective function is mapped into its epigraph. As shown in the SOP formulation on the slide, the scalar t is minimized subject to the constraint that the LC norm of every local current density is bounded by t. This defines a set of Lorentz cones. At the same time, the L infinite error norm is split into a set of simple linear inequalities. Something remarkable is achieved. I have transformed an intractable non-differentiable problem into a smooth second-order cone program which can be solved in polynomial time with absolute convergence guarantees. But as an engineer, I must face the harsh reality of the physical world. For a PCB layout to be manufactured, the milling machine requires a strict minimum spacing between adjacent copper trays to prevent electrical short circuits. This spacing depends on the physical distance between the contour line of the stream function. If the spatial distance constraint is spread analytically and forced inside the optimization core, its beautiful convexity is violently destroyed. The problem becomes an NP hard mixed integer nightmare. My solution to this paradox is an architectural decoupling. The continuous convex conic core is isolated and the discrete parameters, the number of contours, and the file error tolerance are extracted out into an external 2D parametric search space. With the parameters decoupled, the non-convex manufacturing problem can be resolved by performing an iterative parametric sweep. An exhaustive grid search is executed over the 2D parameter space. For each discrete value of the relative error tolerance, the internal conic solver acts as a deterministic operator that maps this tolerance to a unique globally optimal state vector. Because the underlying conic core remains strictly convex, every single subproblem in this grid search is solved in polynomial time with absolute reliability. This completely bypasses the combinatorial exposition and local minima that place standard mixed integer solvers. Physically manufacturing constraints are evaluated ex post, meaning after the continuous optimization is complete. For each optimal state vector generated during the sweep, and for each target contour resolution, a nonlinear spatial distance operator is applied. This operator calculates the minimum physical gap between the resulting contour lines. This data is compiled into a two-dimensional performance vector containing the file error and the physically traced gap. Finally, a strict viability filter is applied. If the calculated gap is smaller than the factory minimum required, the solution is instantaneously discarded as physical unrealizable. The viable candidate design that survive this exposed filtering are then compiled to construct a Pareto frontier. By definition, no design on the frontier is dominated by any other in all objectives. To make a final decision, a Pareto chart is used to illustrate the various solutions by comparing the space between the track or coil contours and the maximum error incurred. Based on this Pareto form, the user can select the optimal solution for the case study according to the criteria of minimum separation and acceptable error. Let us examine the result of this methodology. The slide displays a visual comparison between two synthesized coil layouts. On the left is a conventional design generated using a standard unconstrained inverse method. Notice how the copper trays are forced to crowd together and violate the factory's minimum gap rules. On the right is the proposed optimal design. Thanks to the minimax formulation, the current density is distributed evenly across the surface. The trace spacing is regular and controlled, strictly respecting the minimum manufacturing gap while maintaining a highly efficient magnetic profile. To verify that the manufacturable layout doesn't compromise electromagnetic performance, the quality of the generating magnetic file is analyzed. The plot on the left shows the spatial homogeneity of the file within the central region of interest. Despite enforcing strict manufacturing limits exposed, the optimal layout preserves high file fidelity, achieving extremely low deviation. This performance is exceptionally close to the theoretical unconstrained optimum. This confirms that my parametric decoupling strategy successfully bridged the gap, allowing for a physically robust PCB layout without sacrificing the precision required for the quantum calibration or medical imaging. In conclusion, I have presented a rigorous, mathematically sound framework to synthesize biplanar electromagnetic coils. The key contributions are threefold. First, I introduced a major paradigm shift, replacing a slow and complex combinatorial wave routing algorithm with a continuous convex state estimation formulation. Second, I successfully resolved the manufacturing paradox using an ex-post parametric decoupling strategy, ensuring that all analyzed solutions are totally manufacturable using a standard PCB fabrication process. Finally, these methods enable direct, automated PCB fabrication, taking target file specifications and converting them directly into standard manufacturing files. Thank you very much for your time and attention. I am now open to any question or comment you might have.